Hi, my name is Kobe. Today is lecture 3. We'll be discussing convolutional neural net and recurrent neural networks. First, let's see what we'll cover. We will be discussing basics of recurrent neural networks, and then we will talk about two variants of RNN, namely long short-term memory and gated recurrent unit. And lastly, we'll be discussing how the RNNs have been used in different downstream applications. For the second part of the lecture, we'll be discussing CNN. First, we will cover basics of convolutional neural networks. Next, we'll be discussing a few variants, such as ConvNeXt, ResNet, ResNeXt, DenseNet, UNet, MobileNet, etc. And we will end this lecture by discussing how CNNs have been used in different downstream applications. So first, let's talk about the basics of recurrent neural networks. So let's look at a simple diagram of recurrent neural network. On the left-hand side is a diagram, and on the right-hand side, we show how this diagram can be unfolded. At each time step, suppose we have the hidden state ht-1, and we have the input xt. We combine them using some function f to get the next hidden state ht. Now let us look at the mathematical formulations for RNN. So ht equals to the hyperbolic tangent of whh multiplied by ht-1 plus wxh multiplied by xt and plus some bias. So here we have two matrices, whh and wxh. ht-1 represents the information at the previous step in the sequence. It's a vector that stores the learned information up to that point. xt represents the new input data at current time step, and ht represents the next hidden state calculated based on a weighted sum of ht-1 and xt. Now we'll talk about some problems of vanilla RNNs. The first one is called gradient vanishing. These issues arise due to the multiplication of gradients through the many layers of an RNN due to backpropagation. So if we look at the curve of hyperbolic tangent, it looks like this. If we look at the derivative, we can see that it's always less than or equal to 1. This means that when we multiply many numbers that are less than or equal to 1, it will approach 0. Vanishing gradients make it hard for the model to learn because updates to the weights become insignificantly small. Exploding gradients can cause the weights to oscillate or diverge wildly, so it's a less serious problem than gradient vanishing. Another problem which is related is called long-range memory. RNNs ideally should remember information from early in the sequence to use much later, which is crucial for tasks like text translation or sentiment analysis. However, with vanishing gradients, the network tends to forget this early information. Prediction drift. This is a problem over long sequences. Small errors can accumulate in each time step of prediction, causing RNN to drift off course. This drift makes it challenging to maintain accurate predictions in tasks such as time series forecasting or text generation as the sequence progresses, since current input is based on previous input. Now we will discuss the first variant of recurrent neural network, which is called long short-term memory, or LSTM. LSTM uses some special gated structure to control memorization and forgetting in RNNs. This can help mitigate gradient vanishing and facilitate long-term memory. A simple diagram will look like the following in the next page, where we have these hidden states H0, H1, we have some input X1, and we have some output Out1, and we have 3 gates here, output gate, forget gate, and input gates. These gates are essentially different neural networks with single activation functions, which outputting values between 0 and 1. They are trained to selectively allow information to pass through, which helps in retaining the important information over longer periods and hence mitigating the vanishing gradient problem. Now we will look at some practical information implementation of LSTM. So here we have CT, HT-1, HT and have some input XT and hidden state HT. And we have various functions such as FT, IT, C hat T, and OT. So here, hidden state HT is called self state CT. The output YT is called hidden state HT. And we have the following update equations. Input gate IT simply combines the input XT and previous hidden state HT minus 1. Forget gate FT simply combines the input XT and also the previous hidden state. And similarly, output gate, the process input function C tilde computes the combination of XT and HT minus 1 and apply the hyperbolic tangent activation function. Cell update simply multiply FT by CT minus 1 and add that to IT multiplied by C tilde. And finally, output YT equal to HT and equal to OT multiplied by hyperbolic tangent of CT. Here, let's look at different rows of gates in LSTM. The input gate simply controls the extent to which a new value flows into the cell state. The forget gate determines the information to be discarded from the cell state. The output gate regulates the amount of information to output from the cell state. And the process input C tilde creates a vector of new candidate values that could be added to the cell state. And let's continue. Cell update CT, which updates the cell state by combining the old state influenced by the forget gate and the new candidate values, which is modulated by the input gate, and this is sort of called memory. Output gate, which determines the next hidden state based on the cell state and output gate. The network can selectively remember a forget information, and this will help to preserve long-term dependencies. Now let us look at another variant, which is called gated recurrent unit, or GRU. This type of network is designed to simplify LSTM. Here in the diagram, we can see that there's no cell state, and we only have 2 gates instead of 3. And this means that we will have fewer weights, and it will be faster to train GRU than LSTM. Update equations. So update simply means input plus forget. So the reset gate RT is a weighted combination of the input XT and previous hidden state HT minus 1. Update gate ZT, which is also a combination of input XT and previous hidden state HT minus 1. This gate controls how much input we pass. And we have the process input gate, which is H tilde T, that equals to the combination of XT and HT minus 1. And the HT minus 1 will be multiplied by RT. And the whole calculation will be passed to a hyperbolic tangent activation function. And finally, we have hidden state update, which is simply 1 minus ZT multiplied by HT minus 1. And we add that to ZT multiplied by H tilde T. And output YT is equal to HT. Now let's discuss rows of different gates in GRU. The reset gate RT determines how much past information to forget, allowing the model to drop irrelevant information from the past. Update gate ZT balances between the new input and the past memory, controlling how much of the past state to retain versus the new input. And the process input gate generates candidate values for new hidden state influenced by the reset gate. Hidden state update combines the old hidden state, which is modulated by 1 minus ZT, and the new candidate values weighted by ZT to form the new hidden state. And finally, output YT equal to HT. The updated hidden state serves as the output, representing the current memory of the network. Now let us compare long short-term memory with gated recurrent unit. As we have discussed, LSTM are more complex with 3 gates, namely input gate, forget gate, and output gate, while GRU only have two gates, which is the reset gate and the update gate. Memory usage. LSTMs generally require more memory due to their complexity because they have more ways to train. And similarly, training times, GRU being simpler, often train faster than LSTMs. And performance. According to some studies, GRU might perform better on smaller dataset, while long short-term memories often excel on datasets with longer sequences. In terms of parameters, LSTMs have more parameters, making them more flexible, but they are more prone to overfitting on smaller datasets. In terms of state update mechanism, long short-term memory have separate cell and hidden states, whereas GRU only have a single hidden state. In terms of the choice of model, the choice between GRU and LSTM really depends on your specific application and dataset characteristics. Now let's talk about some advantages of GRU. The first one is faster training. Due to fewer parameters, gated recurrent units can be faster to train, making them more efficient for smaller datasets or when computational resources are limited. The second advantage is that it is efficient on smaller datasets. GRUs may perform better than LSTMs when the amount of data is small because they can capture dependencies without the need for extensive data. And the last advantage is flexibility in memory management. GRUs are capable of adapting to the use of short-term memory through their update and reset gates, potentially capturing more information across various time steps efficiently. Now let's compare vanilla RNN with long short-term memory and gated recurrent units. So the experiment we do is called sequence modeling. In this experiment, we are trying to maximizing the log likelihood of a model given a set of training sequences. And here theta is a set of model parameters. So here we are maximizing the expression 1 divided by n. So here n is the number of sequences. So we are simply taking the average loss. And the loss for each sequence is computed as a summation from t equal to 1 to the time step tn, and summation of log probability of xtn given all the previous elements x1n all the way to xt minus 1n and theta. So since here xtn is a probability vector, and we will take the softmax to make the probability distribution more smooth, and we take the sum of the log probabilities. In the experiment, we will evaluate these units in the task of polyphonic music modeling and speech signal modeling. So here is the results. But first, let's take a look at the number of units for each type of neural network. For long short-term memory, we have 36 units, and the parameters for polyphonic music modeling is roughly 19.8 times 10 to the power of 3. And for gated recurrent unit, we have 46 units and 20.2 times 10 to the power of 3 parameters. For the simple vanilla recurrent neural networks, we have 100 units, and the number of parameters is roughly equal to 20.1 times 10 to the power of 3. For the second task, which is speech signal modeling, the long short-term memory has 195 units, and the number of parameters is 169 times 10 to the power of 3. For gated recurrent unit, we have 227 units, and the number of parameters is 168.9 times 10 to the power of 3. And for the regular RNN, we have 400 units, and the number of parameters is 168.4 times 10 to the power of 3. So you can see that LSTM and GRU require less number of units than the regular RNN, and the number of parameters are comparable. Now let's look at the results. For the music dataset, they have 4 Nottingham JSP chorales, Muse data, and piano MIDI. We have the average negative log probabilities of the training and test sets, which means the lower the number, the better. So in terms of the music dataset, for the regular RNN, the training, for example, the average negative log probabilities is 3.22, and the GRU is 2.79. Long short-term memory is 3.08. And for test dataset, the hyperbolic tangent achieved a negative log probability of 3.13, and GRU has 3.23, and LSTM has 3.20. And we can compare, for example, the music dataset for Nottingham 10H for the regular RNN has the best performance, and for the rest 3 datasets in the music part, the GRU perform best. You can see that the performance are quite similar for these 3 types. However, if we look at a more complicated dataset, which is the speech recognition, the Ubisoft datasets, for example, in the Ubisoft dataset A, LSTM achieved a performance of 2.70, which is much less than the regular RN, which has the performance of 6.44. And for the second Ubisoft dataset, the gated recurrent unit achieved a average negative log probabilities of 0.88, which is much lower than the regular recurrent neural network, which has a performance of 7.62. So you can see that with gating units outperform the one without gating units on the task of speech recognition. For the music dataset, the performance are relatively similar. Now let us discuss downstream applications of RNN, specifically machine translation. So before we talk about machine translation, let's discuss the concept of attention. Attention is a mechanism for alignment in machine translation, image captioning, etc. So in machine translation, attention means we align each output word with relevant input words by computing a softmax of the inputs. Specifically, we have a context vector, Ci, which is a weighted combination of all the hidden states. Aij is called an alignment weight, which is between the input encoding and Hj and output encoding Si. And we can compute this as follows. Aij is equal to the exponential of alignment between Si minus 1 and Hj divided by summation of all the alignments between Si minus 1 and Hj prime. You can see that this is basically a softmax. And now we can have a diagram. So the encoder part, which is the x1 and the h1, and the decoder part simply is the s1 and the y1. So let's say we are computing the s3, which is a hidden state for decoder part. It is simply equal to a weighted average of all the hidden state from h1, h2 all the way to ht. And we have the weights matrix A31, A32, all the way to A3T. Now we can look at some results with bidirectional RNNs, LSTM units, and attention. Here we are looking at a BLUE score, which is bilingual evaluation under study. This is the percentage of translated words that appear in ground truth. So here we have 3 curves. RNN search 50, RNN search 30, RNN ENC 50, and RNN ENC 30. Here the search means they use attention, and ENC means they do not use attention, and 50 and 30 represent the sentence lengths. So in this figure, we can see the BLUE scores of the generated translation and the test set with respect to the length of the sentences. The results are the 4 test set, which includes sentences having unknown words to the models. So here we can see that the RNN search or with attention outperforms the translation mechanism without attention. Now let's show some examples of alignment. So for example, let's say we are translating the sentence, the arrangement on the European Economic Area was signed in August 1992, and we want to translate to French. So here, the brighter the box means more correspondence. So for example, agreement is related to the French word accord, or for example, on is related to the French word sur. And we have another example. It should be noted that the marine environment is the least known of environments. We also have the brighter box means more correspondence between the input word and the translated output words. Now let's discuss another concept, which is called local attention. Previously, if we look at the diagram, S3 attends to all the hidden states, H1 to HT. Now let's look at two forms of local attention, which means we only attend to a specific part of the input. So one mechanism is called monotonic alignment, or local M. This assumes source and target sequences are monotonically aligned, and the line vector is computed as discussed on a previous slide. So simply, for example, S3, we will compute some weighted average, let's say H2, H3, H4. This is called a window that is centered on H3 and has some width, let's say width 1. Or we can have another type of local attention, which is called predictive alignment, or abbreviated as local P. This predicts an alignment position as follows. PT equal to S multiplied by the sigmoid of VPT multiplied by the hyperbolic tangents of WP HT. So here WP and VP are learned model parameters, and S is the source sentence length. So here we simply predict, for example, S3 is, let's say related to the input word X2. So we will put the center of the window to H2. So we will use this align position to form a window of length 2 times t, and we are only attending to this window, pt minus d to pt plus d. Now let's look at more result. So here we are translating between English and German. So it's a WMT14 English-German results. Shown here are the perplexity PPL and tokenized blue scores of various systems on News Test 2014. We highlight the best system in bold and give progressive improvements in italics between consecutive systems. Local P refers to the local attention with predictive alignments, and we indicate for each attention model the alignment score function used in processes. So here, for example, existing NMT system such as RNN search with some unknown replace. Unknown replace means we have translated word that is not in the vocabulary. And ensemble of 8 models simply means we have 3 models that predict the output and we combine them together. And the new system proposed by the author, for example, the base plus reverse. Reverse means we reverse the input sentence, and dropout means we ignore part of the neural network. And we have global attention, and we have some feed input or unknown replace. And finally, the ensemble of 8 models plus unknown replace achieve a blue score of 23.0. Now let's look at some notes on previous table. So we can see that the score of HT and HS can be computed in many different ways. For example, dot product, or more generally, we can insert a matrix WA into the expression, or you can use the concatenation, which is some matrix VA transpose multiplied by hyperbolic tangent of WA, and WA multiplied by concatenating HT and HS. Or we can use the location score, which is equal to the softmax of WA multiplied by the hidden state HT. So hidden input feeding in the previous result means attentional vectors HT are concatenated with inputs at the next time steps. And here we limit our vocabularies to be the top 50K most frequent words for both languages. words not in this shorted list of vocabularies are converted into a universal token UNK. Now let's look at more examples of global, local attention, local M and local P. And so, for example, the first one is the global attention, which you can see has many spot that is not black. For the local M attention or monotonic, we can see that the attention, we have seen that there are less boxes that are bright because we are only attended to a small window. And here is the local attention, which use some neural network to predict the position. And golden alignment simply means what is the output words that is aligned to the input words, the true alignment, roughly speaking. And now let's summarize our recurrent neural network part of the lecture. So we have introduced RNNs for processing sequences. We have discussed mathematical formulations of RNNs, including input, hidden state, and output. And we have discussed some challenges of RNNs, such as gradient vanishing and explosion. We have talked about solutions to the above RNN challenges, namely long short-term memory, LSTM, and gated recurrent unit GRU. So LSTMs and GRU structures are mechanisms to come back to vanishing gradient problem. And the differences, we also talk about the differences between LSTM and GRU in terms of complexity, memory usage, and performance. So LSTM uses more memory because they have 3 gates. GRU uses less memory, which performs better on smaller datasets. And we also talk about the applications in real-world scenarios, such as language modeling, speech recognition, and machine translation. And that's it for the RNN part. And for the next part, we will be discussing convolutional neural networks. Welcome back. For the second part of the lecture, let's talk about convolutional neural networks. So first, let's look at the basics of convolutional neural network. So for instance, let's look at an image of 5 by 5. Each value in this matrix represents the value of the pixel, for example, 0. And let's say we take a part of the image, 778, 251, 131. We multiply by a kernel of size 3 by 3. Let's say 121, 021, 211. And we do matrix element-wise multiplication. And we sum the values. Let's say we get 46. And we insert 46 into a results matrix. Another operation is called polling operation. Here we simply take the max value of the submatrix, let's say 8, and we insert 8 into the position of the new matrix. Before we talk about the variants of CNN, let's look at highway networks. This is a type of image classification network that is designed to mitigate issues associated with training deep neural networks, such as gradient vanishing. This is accomplished through the use of a learned gating mechanism for regulating information flow, which is inspired by long short-term memory recurrent neural networks, which is covered in the previous part. In highway networks, information either flows without attenuation or flows using neural network weights. Now let's look at the mathematical formulation. Specifically, Y output is equal to H, which is a neural network that takes the input X and then the matrix WH. We multiply this H by a T called transform gate, which is applied on X and some matrix WX. We add this to another gate C called carry gate, which is simply X times CX WC. So for simplicity, we often set C equal to 1 minus T. Then Y is simply equal to H of X times T of X plus X multiplied by 1 minus TX. Here, Tx is defined as the sigmoid of Wtx plus Bt, where sigmoid x is defined as 1 divided by 1 minus e to the power of minus x. Now let's discuss the advantages of highway networks. For example, a highway layer can smoothly vary its behavior between that of a plane layer and that of a layer which simply passes its input through. So to analyze this, so let's say the transform gate T is set to roughly 0, then we can see that the first part of the output disappear, and for second, we simply have y equal to x. And let's say if T is really close to 1, then the second part disappear, and this part is really just y equal to h of x, which is a plane layer. So a simple initialization scheme which is independent of the nature of h, BT can be initialized with a negative value such as -1, -3, such that the network is initially biased towards carry behavior. Note that a highway network consists of multiple blocks, such that the ith block computes a block state HIX and transform gate output TIX. Finally, it produces the output YI, which is H multiplied by T, plus X multiplied by 1 minus T. And all of this is connected to the next layer. Experiments. Here we compare the optimization of deep plane networks and highway networks using the MNIST image dataset. For networks, we have varied depths, 10, 20, 50, 100 layers. They are trained to observe optimization performance. Highway networks displayed consistent performance across all depths, as we'll see in the next page, contrary to plane networks whose performance degraded with increased depths. Notably, a 100-layer highway network significantly outperformed a 10-layer version. This study also introduced a preliminary test on a 900-layer highway network on CIFAR 100, which showed promising results without optimization problems. So here, let's look at the result. The x-axis is number of epochs, the y-axis is the mean cross-entropy error, and the blue curve is the plane neural network, red curve is the highway network. All networks were optimized using SGD with momentum, and the curves shown are for the best hyperparameter settings obtained for each configuration using a random search. Plane networks becomes much harder to optimize with increased depths. For example, depth 100, you can see the loss is much higher for plane networks than that of a highway network. Similarly, for 50 and 20. For depth 10, the plane network actually has a better performance than highway networks because it's simpler. Now let's do more experiments. Here we compare highway networks to FinNets on CIFAR 10, which is another image dataset for evaluating generalization in supervised learning. FinNets require complex training procedures. They use a teacher network for networks deeper than 5 layers with a limited number of parameters and operations. Highway networks were easily trained with parameters and operations just like FinNets, but they only use straightforward backpropagation instead of two networks. This approach to training highway networks proved effective even for deeper and thinner network architectures. Now let's look at results. The FinNet results, we have teacher networks, 5 layers, and different FinNets networks with invariant number of layers. And we have a corresponding highway networks, highway 1, 2, 3, 4, with the number of layers 11, 19, 19, and 32. And the number of parameters are much less than that of the FinNet. But the accuracy are comparable. So FinNets are trained using a two-step training procedure using soft targets from the trained teacher network, and this is trained using backpropagation, but highway networks is trained directly using backpropagation. Star means networks that were trained only on a set of 40,000 out of 50,000 examples in the training set. Now let's look at many variants of the CNN. The first is learn at 5. This is a sigmoid activation after each convolution operation, and they use average polling. It takes the average. So here we start with a 28 by 28 image. We start by doing a convolution, and we obtain 6 feature maps. We do polling, which reduce the size. We do another convolution, another polling, and finally we connect that to a dense layer, another dense layer, followed by the last dense layer, which output 10 probabilities. In order to make the probabilities, we use the softmax activation at the end of the last dense layer. Now let's look at a very important ImageNet dataset. This is a dataset with over 15 million labeled high-resolution images belonging to roughly 22,000 categories. Here we have seen different categories such as vehicle, craft, watercraft, sailing vessel, sailboat, trimaran, etc. Now let's look at another variant called RxNet, which is can we train larger, deeper convolutional neural network using GPU? The issue for a larger training dataset, simply we can just use ImageNet. If in terms of computational resources, we simply implement RxNet on GPU. And this is the first work that uses GPU to train a deep neural network. And here are the technical details. We have 5 convolution layers, 3 fully connected layers. We use ReLU activation plus layer normalization after each convolution layer. We have 3 max poly layer, and the dropout is 0.5 for the 2 hidden fully connected layers. Dropout means we skip some units in the neural network. Now let's look at another variant, which is called VGG-Net. Here we want to investigate what's the effects of increasing depths of deep CNN network. The main contribution is they design a VGG CNN block that can easily increase the depth by stacking blocks. In each VGG block, we have convolutional 3x3 followed by a few of convolutional 3x3, and we follow that with ReLU activation and 2x2 max polling with stride 2. Stride is the number of pixels we move from the one window to the next, and we can easily stack these VGG blocks together, and we follow that by fully connected layers as usual. Then now let's have some results. So ConvNeXt configuration A, B, C, D with different number of weight layers. The last configuration E has 19 weight layers, which is the most number of them. And we can see the architecture. For example, E, we have conv3 64, followed by another block of conv3 128, followed by conv3 256, followed by conv3 512, and followed by conv3 512. And do max pooling and fully connected layer and softmax. And in table 3, we list the ConvNeXt performance at a single test scale. You can see that the configuration E achieved the lowest top 1 validation error and top 5 validation error. And the next variant we'll look at is called ResNet. This is proposed in 2015. Here we are investigating is learning better networks as easy as stacking more layers. Here we have issues as we have deeper neural networks such as vanishing exploding gradients. This can be addressed by batch normalization. And the second issue is performance degeneration on deeper networks. This is an open problem. And here we assume that there exists an identity mapping from deeper to shallower layers. And we know that it's easier to learn residual mapping instead of the identity mapping. The solution is to add residual connection to the CNN network. So here, the plane network, we simply progress normally. However, for the residual network, XL is computed by fxl-1 plus xl-1. So, for example, xl-1 is directly connected to XL. So in the following diagram 2, we have residual learning. X is passed by weight layer, passed by ReLU, another weight layer, and X has another connection, the X identity, which is simply added to fx, and then we apply a value. The results, the performance degeneration for deeper networks is gone, and deeper ResNet comes with better performance. Here we have a figure 4, which is training on ImageNet. This curve denotes the training error, and bold curve denotes validation error of center crops. Left is the plane network's 18 and 34 layers. Right is ResNet of 18 and 34 layers. In this plot, the residual network have no extra parameters compared to the plane counterparts. We can see that they have a lower error than the plane counterparts. Now let's look at the error rate. For a 10 crop testing on ImageNet validation, VGG16 is based on our test. ResNet 5, 50, 101, 152 are of option B. that only use projection for increasing dimensions. We can see that the ResNet 152 achieved the lowest top 1 error and also the lowest top 5 error. Now let's look at DenseNet, which is proposed in 2016. What if we extend the residual connection across all layers? This is a logical extension of ResNet, since we can simply add connections from XL to XL-1 to XL-2, etc. to the first unit. So plain network, we have XL equal to FXL-1. ResNet, we simply add XL-1. And DenseNet, we have a function that applies to all the previous layers, X0, X1, X2, and XL-1. So DenseNet also introduced a technique called dense block, which is batch normalization, followed by ReLU, followed by 1-by-1 convolution, followed by batch normalization, followed by ReLU, followed by conv 3-by-3. This is a basic block. They introduced a new convolution, 1-by-1 convolution, as a bottleneck layer to reduce the number of inputs. Transition layer, which is the 1-by-1 convolution, followed by 2-by-2 average polling. Here, they introduced 1-by-1 convolution to halve the number of input features. So here we have a figure, a deep dense net with 3 dense blocks. The layers between 2 adjacent blocks are referred to transition layers, and they change feature map sizes via convolution and polling. We have input, followed by convolution, and then dense block 1, followed by transition layers, consist of convolution, polling, and dense block 2, dense block 3, etc., followed by the last few linear layers and the prediction, which is a course. Now let's look at the results. Here in figure 3, we are comparing the DenseNet and ResNet top 1 error rates, single prop testing, on the ImageNet validation dataset as a function of learned parameters and flops during test time. The red curve is ResNet and the blue curve is DenseNet. We can see that DenseNet has a validation error for both, a lower top 1 error rates and a lower number of floating point operations. So fewer parameters and fewer computational resources. And DenseNet get the same or better error rate compared to ResNet. Now let's look at the next variant, which is called GoogleNet or Inception. This is proposed in 2014. And we investigate, what if we make the CNN network wider instead of deeper? Larger model leads to better performance but higher computation cost. Fully connected architecture layer, we can also use sparsely connected architecture, which is wider. And we ask, what is the optimal local sparse structure of the CNN block? For example, the kernel size, polling, etc. The solution is to let the model learn. We have a previous layer followed by a wide network 1-by-1 convolution, 3-by-3 convolution, 5-by-5 convolution, 3-by-3 max polling, and we follow that by filter concatenation. So to reduce cost, they introduced a 1-by-1 convolution layer before the high-cost convolution 3-by-3, and convolution, and also they use convolution 1-by-1 before convolution 5-by-5. This can reduce the computation cost. This is called the split transformation merge strategy. And the results, we can see that in the year 2014, GoogleNet placed the first place, which have a 6.63% of error for the top 5, and they do not use external data. And the next variant proposed in 2016 is called ResNeXt. And the question we ask is, can we develop a wider ResNet? Let's say we apply split transformation merge strategy with the same topological branch or VGG style repeating layers. So we have 32 number of them, a wide network, and we apply a residual connection between each block. To the left is a block of ResNet 14, and the right is a block of ResNeXt with cardinality 32, with roughly the same complexity, and the layer is shown as the number of input channels, filter size, and number of output channels. The results, so the left table, we show the number of parameters and the number of floating operations. We can see that ResNeXt achieved lower error rate with the same number of parameters. And here we can also see the structure that is used in ResNet 50 and ResNeXt 50, 32 by 40. And for table 3, they have done the ablation experiments on ImageNet 1K. The top is ResNet 50 with preserved complexity roughly 4.1 billion flops, and bottom is ResNet 101 with preserved complexity about 7.8 billion flops, and error rate is evaluated on a single crop of 224 by 224 pixels. You can see that ResNeXt 101 and ResNeXt 50 has a lowest top line error for the setting of 32 by 40. Next, we can look at ConvNeXt, which is a new approach proposed in 2022. Now we want to bridge the gap between convolution and neural net and transformers. So for sometimes the region transformer and the swing transformer has been the state-of-the-art performance for visual model backbone. And we ask, is convolution neural networks really not as good as transformer models? So the author investigated by start with ResNet 50, but re-implement the CNN networks with model designs. The results show that ConvNeXt achieves better performance than the VIT models again. So modern design include use ResNeXt, apply inverted bottleneck, use larger kernel size, and have different training strategies. For example, using 300 epochs rather than 90, and using Adam optimizer, and use data augmentation like mix-up, card mix, and use regularization schemes like label smoothing. And the macro design change include changing stage compute ratio, changing stem to Apacheify, and change value to GELU, and having fewer activation functions, fewer normalization layers, and change batch normalization to layer normalization, and separate downsampling layers. And lastly, let's look at CNN for downstream application. Downstream tasks include image segmentation using UNet, object detection using YOLO, and we have CNNs that are more cost-effective, such as MobileNet, SqueezeNet, etc. So UNet is proposed in 2015, which is a fully convolutional neural network for image segmentation. Here, the output is two segmentation map that representing the probabilities of each pixel belongs to either a background or the object. So we simply, for example, try to predict which pixel belongs to a person, which pixel belongs to a bicycle, and which pixel belongs to a background, etc. So here we have a figure, the UNet architecture, example for 32 by 32 pixels in lowest resolution. Each blue box corresponds to a multi-channel feature map, and the number of channels is denoted on top of the box. The XY size is provided at the lower left edge of the box. White boxes represent copied feature maps, and the arrows denote the different operations. Here we have up convolution. Vanilla convolution reduces the size of feature map, and up convolution increases the size of feature map. And we have a matrix called intersection over union, which is equal to the area of intersection divided by area of union. This achieves the state-of-the-art performance as shown in table 2. Segmentation results IOU and the ISBI cell tracking challenge in 2015. UNet achieved a PhD U373, they achieved a 0.92 accuracy on the PhD dataset. And for the next dataset, they achieved a 0.7753 IOU score. Now let's look at another variant called MobileNet, which is introduced in 2017. This is an efficient network with stepwise separate convolution. In vanilla convolution, let's say we have some steps of 3. We compute the CNN on each layer, and then we aggregate them together. The cost is equal to WK multiplied by HK multiplied by the Cin. This is the kernel size, and the number of kernels is equal to Cout, and output feature size is Wout multiplied by Hout. Now we introduce stepwise separate convolution, which is first we do depthwise convolution, we do not aggregate, and then we do pointwise convolution, and then we aggregate. And pointwise convolution, we simply multiply each element in the matrix or each pixel value by some number, and the computational cost for depthwise convolution is equal to WK multiplied by HK, multiplied by C in, multiplied by W out, multiplied by H out. This saves the cost of 1 divided by C out. In terms of pointwise convolution, we have 1 times 1 multiplied by C in, multiplied by C out, and W out, H out. You can see that this speeds up by 1 divided by WK times HK, and we can add the two speed up together. Now we have a figure 3. The left is a standard convolutional layer with batch norm and ReLU, and right is stepwise separable convolutions with stepwise and pointwise layers followed by batch normalization and ReLU. And the result as follows. In table 8, we show different models comparing to other popular models such as GoogleNet and VGG 1.6, VGG 16. You can see that the accuracy on ImageNet for the mobile net is roughly comparable to other models, but they have only 569 million multiplication additions, which is much less than GoogleNet and VGG 16, and they also have less number of parameters. For a smaller mobile net comparison, they actually have a higher accuracy than SqueezeNet and RNNs, with much less number of multiplication additions and much less number of parameters than RNNs. Now let us summarize the CNN part of the lecture. We first introduced highway network, which is an early attempt at image classification. LeNet 5 is the first CNN network. ResNet is the first CNN network on GPU. VGGNet introduced a increasing model depth via repeating blocks. ResNet introduced residual connection that enabled deeper network. DenseNet introduced residual connection across all layers. GoogleNet Inception introduced its wider network via split transformation merge. ResNeXt introduced its ResNet with VGG-style split transformation merge, and ConvNeXt introduces CNN network with modern design techniques. UNet introduces CNN network for image segmentation. Finally, MobileNet introduced more cost-effective CNN network via depth-separate CNN. And now let's look at a timeline of different types of CNN. Before 2012, we have LeNet 5. 2012, we have ResNet. 2014, VGGNet. 2015, ResNet. 2014, we also have GoogleNet. 2016, we have DenseNet. 2020, we have ConvNeXt. And now we are going towards deeper networks and deep wider network. For downstream application, we start with UNet, image classification, MobileNet, which makes computation more efficient, YOLO, which is for object detection, SqueezeNet, smaller size, and many other downstream tasks. And that's it for the CNN part of the lecture. And this also concludes lecture 3. We have covered both recurrent neural network and convolutional neural network. Thanks for listening.